Okay, now I would like to introduce you to the guts of the Orthohack preprocessor, which is something that I call hierarchical ratio analysis. Hierarchical, of course, means there is some kind of inheritance structure, like a tree structure. Ratio is, of course, the quotient, in this case, between two different numbers, and it is a form of numerical analysis. And the first stage is really what we call a binomial discovery, and this is how this works. So let's say that you have a signal. Here it consists of 6 sample points labeled S0 through S5. And then we have a bunch of orthobasis vectors. If it's a normal orthobasis, normal is a bad word, if it's a typical orthobasis transform, then most likely we would have 6 sample points in each one of these orthobasis vectors. I've just shown you the first 3. And you can see graphically, here's the 0 line, graphically what these orthobases look like. And this is the algebraic expression for multiplying each of these orthobasis samples with the corresponding signal sample point and then adding them together. So you see, for example, x0 is -2, x1 is 2, x2 is -2, and so forth. And so we get these expressions for the coefficients C0, C1, C2, and so forth. And what we want to do is we want to look at the ratio of this coefficient to this coefficient. So in this case, if we take -2 divided by 2, we get -1. Down here, if we take -4 over 1, we get -4. So we look at the ratio of the coefficient of each of these components between every 2 terms we can choose. So if there are 6 terms, then there are 6 choose 2, which is what, 12, I guess? Yeah, 12 different combinations we need to look at. And as you can see, this kind of blows up in an n squared way, which is why this is rather computationally expensive when we're dealing with 1,000-point orthobases and whatnot. But there you have it. That's how we do it. We look at all the different possible combinations of terms and the ratio between them, and we try to find at least one pair of terms that is repeated in more than one orthobasis. And we have ways of prioritizing which such binomials are more important than others, and I'll go into that in the next video. But suffice to say, if you look here, okay, we can factor out this 1. In other words, we have -4S0 plus S1, and if we do that, then we have a factor of 2 out here, and we have the same -4S0 plus S1. So what does this mean? Well, this means that if we want to compute the transform just slightly faster and save a couple of operations, basically we can define this term. We can take -4 times S0 and add S1, and we can call it S6, which is a virtual sample, if you will, S6. And when we make this substitution, then down here, instead of multiplying 8 by S0 and 2 by S1 and adding them together, all we have to do is multiply 2 by S6. And certainly when you start getting to 3, 4, and 200 repetitions of the same binomial, you start to save a lot of time. And in the next video, I'll tell you about how we nest all of this to create an actual compute tree.